magnetic breakthrough, detecting signals in non-magnetic metals for faster processes. Imagine a breakthrough that could revolutionize the way we understand magnetism in metals, potentially leading to faster processes and more efficient technology. Researchers from Hebrew University, in collaboration with experts from the Weizmann Institute, Pennsylvania State University, and the University of Manchester, have made a remarkable advancement in the field of magneto-optics. They have successfully enhanced the magneto-optical Kerr effect, MOKE, technique by utilizing a 440 nanometer blue laser combined with modulated magnetic fields. This innovative approach has allowed them to detect magnetic signals in non-magnetic metals such as copper, gold, aluminum, tantalum, and platinum, an achievement that was once deemed nearly impossible. This non-invasive method not only opens new avenues for exploring magnetism but also holds the promise of contributing to the development of faster processes, more efficient systems, and improved sensors. It builds upon Edwin Hall's pioneering work from 1881, where he attempted to measure the Hall effect using light but faced challenges due to insufficient signal strength. #unveiling subtle magnetism. The researchers have significantly upgraded the MOKE technique, which traditionally uses a laser to measure changes in light reflection caused by magnetic fields. By integrating a 440 nanometer blue laser with large amplitude modulation of an external magnetic field, they have enhanced the sensitivity of this method. This advancement enables the detection of magnetic echoes in non-magnetic metals, a feat that was previously thought to be unattainable. In conventional practices, measuring the Hall effect, a fundamental tool in semiconductor technology and materials science, requires physically attaching wires to a device. This process can be cumbersome and challenging, especially when dealing with components at the nanometer scale. However, the newly developed technique simplifies this process significantly. It only requires directing a laser beam onto the electrical device, thus providing a non-invasive means of analysis. Upon further investigation, the researchers discovered that what initially appeared to be random noise within the signal was actually patterned and related to a quantum property known as spin-orbit coupling. This phenomenon connects the movement of electrons to their spin, which is a crucial aspect of modern physics. Understanding this relationship also sheds light on how magnetic energy dissipates within materials, offering valuable insights that could influence the design of magnetic memory, spintronic devices, and quantum systems. #unlocking quantum insights. This study tackles the intricate challenge of detecting minute magnetic effects in non-magnetic materials like copper, gold, aluminum, tantalum, and platinum. The researchers' ability to identify magnetic echoes in these metals by refining the MOKE technique is a significant milestone. Delving deeper, the team found that the seemingly random noise in their signal was not random at all. It followed a distinct pattern linked to spin-orbit coupling. This connection is vital as it affects how magnetic energy dissipates in materials, providing insights that are directly relevant to the design of magnetic memory, spintronic devices, and even quantum systems. The technique offers a highly sensitive, non-invasive tool for investigating magnetism in metals without the need for large magnets or cryogenic conditions. This advancement could lead to breakthroughs in faster processes, more energy-efficient systems, and sensors with unprecedented accuracy. It also presents a fresh perspective on what was previously achievable with traditional methods of magnetic metal detection. The current research has successfully measured what was once thought to be invisible by tuning into the right frequency and knowing precisely where to look. #technological implications. This research builds upon the established Hall effect, a principle that is essential in the semiconductor industry and materials science, by providing a more straightforward measurement process. Traditional Hall effect measurements require the physical attachment of wires to a device, which can be time-consuming and challenging, particularly with nanometer-sized components. In contrast, the new technique only necessitates a laser beam directed at the electrical device. The team's analysis revealed that the seemingly random noise in their signal was actually patterned and connected to spin-orbit coupling, a quantum property that links electron movement to spin. This relationship also influences how magnetic energy dissipates in materials, yielding insights that have direct implications for the design of magnetic memory, spintronic devices, and quantum systems. The sensitivity of this technique allows for the exploration of magnetism in metals without the need for massive magnets or cryogenic conditions. This represents a significant leap forward compared to earlier attempts to measure the Hall effect with light, as Edwin Hall's efforts in 1881 were hindered by the lack of detectable signal strength in silver. The current research has successfully measured what was once considered invisible by tuning into the appropriate frequency and identifying where to look, offering a new approach to magnetic metal detection. But here's where it gets controversial. Could this new method challenge the very foundations of how we understand magnetism in materials? What implications might this have for future technologies? We invite you to share your thoughts and opinions in the comments below. Unlocking the invisible. Scientists detect 150-year-old physics mystery with blue laser. A mysterious magnetic signal in everyday metals finally revealed. For over 150 years, physicists have grappled with a perplexing magnetic signal hidden within common metals like copper and gold. Despite their theoretical understanding, they lacked the means to observe this subtle phenomenon known as the optical Hall effect. That is, until now. A team of innovative scientists has uncovered this elusive magnetic behavior using a simple blue laser and a clever twist on a classic technique. This groundbreaking discovery not only sheds light on the hidden magnetic properties of seemingly silent materials but also opens up new possibilities in the fields of spin physics, quantum technologies, and electronics design, all without the need for wires or extreme conditions. Illuminating the unseen. Detecting faint magnetic signals. The research group, led by PhD candidate Nadav Shalom and Professor Amir Kapua from the Hebrew University, in collaboration with experts from the Weizmann Institute of Science, Pennsylvania State University, and the University of Manchester, has devised an ingenious method to detect extremely faint magnetic signals in everyday metals using only visible light and a refined optical technique. Their findings, published in the journal Nature Communications, could pave the way for significant advancements in technologies ranging from smartphones to quantum computing. The optical Hall effect, a phenomenon predicted to provide insights into electron movement under the influence of both light and magnetic fields, has long eluded scientists due to its subtlety. Despite more than a century of theoretical understanding, this effect has been too faint to detect with visible light, leaving experts in the dark. Professor Amir Kapua likened the challenge to trying to hear a whisper in a noisy room for decades. The solution? A highly sensitive microphone to finally hear the whisper. Cracking the code, a new perspective on the invisible. The researchers focused on the tricky challenge of detecting tiny magnetic effects in non-magnetic materials like copper and gold. While these metals may appear magnetically quiet, they do respond to magnetic fields in extremely subtle ways under the right conditions. To overcome this challenge, the team enhanced a method called the magneto-optical Kerr effect, MOKE, which uses a laser to measure how magnetism alters light's reflection. By combining a 440 nanometer blue laser with large amplitude modulation of the external magnetic field, they significantly increased the technique's sensitivity, enabling them to detect magnetic echoes in non-magnetic metals like copper, gold, aluminum, tantalum, and platinum, a feat previously considered near impossible. The significance: when noise becomes signal. Traditionally, measuring the Hall effect required physically attaching tiny wires to the device, a process that is both time-consuming and tricky, especially when dealing with nanometer-sized components. The new approach, however, is much simpler. It merely requires shining a laser on the electrical device, eliminating the need for wires. Upon further investigation, the team discovered that what appeared to be random noise in their signal followed a clear pattern tied to a quantum property called spin-orbit coupling, which links electron movement to their spin, a key behavior in modern physics. This connection also influences how magnetic energy dissipates in materials, with direct implications for the design of magnetic memory, spintronic devices, and even quantum systems. PhD candidate M. Shalom compared the discovery to realizing that static on a radio isn't just interference, it's someone whispering valuable information. The team is now using light to listen to these hidden messages from electrons. A new window into spin and magnetism. The technique offers a non-invasive, highly sensitive tool for exploring magnetism in metals without the need for massive magnets or cryogenic conditions. Its simplicity and precision could help engineers build faster processors, more energy-efficient systems, and sensors with unprecedented accuracy. Professor Capua emphasized the significance of this research, stating that it turns a nearly 150-year-old scientific problem into a new opportunity. By tuning into the right frequency and knowing where to look, the team has found a way to measure what was once thought invisible. As the scientific community continues to explore the implications of this discovery, one thing is clear: the future of spin physics, quantum technologies, and electronics design is brighter than ever, thanks to a simple blue laser and the innovative minds behind it. Reference: a sensitive MOKE and optical Hall effect technique at visible wavelengths. Insights into the Gilbert damping by Nadav M. Shalom et al., the 17th of July 2025, Nature Communications. DOI 10.1038 S41467-025-61249-4. Revealing Gilbert damping with sensitive MOKE and optical Hall effect techniques. Unlocking the secrets of magnetic materials, a breakthrough in optical sensing techniques. Imagine trying to measure the tiniest vibrations in a storm. That's essentially what scientists face when studying magnetic properties at the atomic level. But here's where it gets controversial. A new technique is challenging traditional methods by using visible light to peer into the hidden world of magnetic interactions. This approach, combining the magneto-optic Kerr effect, MOKE, and the optical Hall effect, OHE, is rewriting the rules of how we understand materials at the quantum scale. And this is the part most people miss. The key lies in how these effects are amplified using a clever setup involving rotating magnets and laser light. Are you ready to dive into the details? Let's explore how this innovation could revolutionize material science. The Hall effect, first discovered in the 1870s, describes how a magnetic field deflects electric currents, creating a measurable voltage. In magnetic materials, this becomes the anomalous Hall effect, AHE, where the voltage is unusually large and saturates with the applied magnetic field. The MOKE, its optical cousin, does something similar but with light. It measures the polarization rotation of reflected light, which is incredibly sensitive, even to a single atomic layer of magnetic material. But here's the catch: measuring the non-magnetic optical Hall effect, OHE, at visible wavelengths is notoriously tricky. Why? Because the electronic displacements needed for a measurable signal are smaller in the visible range compared to lower frequencies like THz or infrared. Recent studies in semiconductors and 2D materials have shown promise, but the real breakthroughs come from metals like copper, gold, and silver. Early experiments used multiple reflections to boost sensitivity, while later methods modulated the polarization of light to detect subtle effects. But these approaches hit a wall when it came to practical applications. Enter the ferrous MOKE technique, a game changer. By using permanent magnets on a spinning disk, researchers achieved high-frequency magnetic field modulation, making OHE measurements at visible wavelengths not just possible but surprisingly precise. This method, named after the ferrous ferromagnetic resonance technique, leverages large-amplitude magnetic fields to enhance sensitivity, much like how a spinning wheel amplifies motion in mechanical systems. But does this always work, or are there hidden trade-offs? Let's find out. The team tested this technique on thin films of copper, gold, aluminum, tantalum, and platinum. Their results? A fascinating link between the noise in their measurements and the spin-orbit coupling, SOC, of these metals. SOC is a quantum mechanical phenomenon where the spin of an electron interacts with its motion, and it's closely tied to Gilbert damping, a measure of how quickly a material loses magnetic energy. In heavier metals like platinum and tantalum, the noise was significantly higher compared to lighter ones like copper. This isn't just a random observation, it's a clue. The researchers suggest that the noise isn't just interference but a direct result of SOC-induced interactions between light and spin. Could this mean we are finally seeing the invisible dance of spin and light in action? And if so, what does it tell us about designing better magnetic materials for technology? The experimental setup is as ingenious as it is simple. Using a polar MOKE geometry, they rotated a disk with permanent magnets to create a modulated magnetic field. A laser beam, polarized in one direction, interacts with the material, and the resulting transverse polarization is detected. By comparing this to traditional methods, they found that the ferrous MOKE technique reduced noise by over 30%, making it possible to detect effects previously buried in measurement errors. But here's a thought-provoking twist: while the Lorentz-Drude model explains some of the data, it falls short in others. For example, the model predicted the OHE response of tantalum accurately but failed for copper and gold. This discrepancy hints at missing pieces in our understanding of electron behavior in metals. Could interband transitions or non-parabolic band structures be the culprits? The debate is just beginning. The implications are profound. By linking optical noise to SOC, this research opens new avenues for studying spin dynamics in non-magnetic materials. For instance, the correlation between the noise levels in platinum and tantalum and their known spin-pumping effects in magnetic bilayers suggests a universal mechanism at play. This could lead to better designs for spintronic devices, where controlling spin currents is key. But is this correlation just a statistical fluke, or does it point to a deeper principle? The authors argue the latter, citing a near-perfect linear fit, R squared equals 0.997, between noise and spin-orbit coupling strength. Yet, skeptics might argue that other factors, like impurities or defects in the materials, could skew the results. What do you think? Should we trust this correlation, or is more research needed to untangle the variables? Looking ahead, the technique's potential is vast. By extending the method to other wavelengths and materials, researchers could map out the intricate dance of electrons and light in topological materials or 2D systems. Temperature-dependent studies could reveal how thermal fluctuations affect these interactions, while advanced detection methods might separate the Kerr rotation and ellipticity components in non-magnetic materials. The future of optical sensing in materials science is bright, literally and figuratively. But as with any groundbreaking work, questions remain. How will this technique handle the complexities of real-world applications? And what other surprises might the quantum world have in store for us? The answers could redefine how we engineer materials for the next generation of technology. What's your take? Share your thoughts in the comments below.